Okay, and now for our second presentation this session, we have Evan Rasch and Carl Kempf from Intel Corporation.
Thank you. Good morning, ladies and gentlemen. I'm Carl Kempf. Evan and I are members of the Decision Engineering Group at Intel Corporation. We're honored to have been invited to present our work on product line design and scheduling in this venue. We'll try to present our material in three sections. I'll give you the background and tell you what the business problem is. Evan will come up and detail the formulation of the problem, our new algorithm, and our custom implementation, and then I'll come back and show you the business impact of the deployment of the system so far. Intel Corporation was founded 43 years ago by Bob Noyce, who invented the integrated circuit, who's the co-inventor of the integrated circuit, and Gordon Moore, whose work refined the manufacturing processes necessary to make integrated circuits in high volume. And it's the work of these two that form the basis of the problem we'll describe to you today. First, the process technology work of Gordon Moore. Gordon quite accurately predicted many years ago that as we continuously improve our manufacturing process, we'll be able to double the number of transistors we can put on a given area of silicon every 2 years. You see a caption from one of our latest press releases for our 22 nanometer process that indicates we can put 6 million transistors now on a period at the end of the sentence, the end of the period that you would see in a newspaper or a magazine, not the monster period that's on the screen here, but that little teeny tiny one. And it's these advances in process technology that drive the innovation of new features in our products and new collections of features to make up our products, and we'll talk about that in some detail. In addition, the product technology, from Bob Noyce's perspective as the co-inventor of the integrated circuit, we now are in a wide variety of markets with a very wide variety of products. You see on the screen from data centers and servers on the left-hand side to laptops and notebooks and desktop computers to ultra-mobility, tablets and cell phones, to embedded in comms devices, the infotainment system in your car, for example, to digital appliances in your home. On the left-hand side of the diagram, we make very high-performance products. On the right-hand side, as you see in the small picture, very compact products. The important thing to notice here is that we are in a wide variety of markets with a wide variety of products. The markets have very different feature requirements, and the markets are quite rapidly, quite fast-moving. The example I would give you is the cell phone, which lately has turned from a communications device to a fashion accessory. I'll try to describe the business problem as a three-dimensional problem. We'll talk for a moment about the marketing aspect, satisfying the requirements of markets. We'll talk about the features and our innovative technology treadmill to come up with new features and new associations of features. And then we'll talk about the dynamics of both of these with the time axis. So to start, I'm looking at the front face of that three-dimensional problem. And in the rows, we have the markets that we service. Each one of the markets in this particular representation takes one product. So there may be 6 or 7 markets in this set that address the cell phone market, from the simple cell phone to the intelligent phone. There may be 5 or 6 markets here that address the overall tablet market with different requirements. In the full Intel problem, you may see 200, 225, 250 separate markets here, each with a forecasted average selling price and forecasted volume. In the columns in this representation, we have the features: single-core processor, dual-core processor, quad-core processor, small memory cache, large cache, memory controller, USB port, simple graphics controller, high-definition graphics controller, motor controller. In fact, if we listed all the hardware features in a sizable Intel problem, we may have 200 or 300 columns here. If we include the software drivers for each one of those, there's at least one software driver for each one to connect the hardware to the operating system. We can easily have a problem with 1,000 columns. each with a engineering cost, both the cost to develop the feature and then the cost to integrate the features together into a product, and of course the manufacturing cost. The cells in the matrix are then the requirements for features for a given market. So we see on this very simple example that market 1 needs 1 of feature 4, market 2 needs 1 of feature 5, et cetera, et cetera. And two intuitive solutions present themselves. One of the obvious ones is, well, why not make one chip with all the features on it and sell the same product to everybody? The economic difficulty with this is the chip would be very big and very expensive. It's not really an economically feasible solution to the problem. The other obvious solution is, well, why not make a custom product for each market? The difficulty there is if there are 250 markets, we don't have the engineering resources to engineer that many products. So the interesting problem becomes, what set of products should we make? Fairly intuitive from the example in front of you that you could service market 1 and 2 with one product that has features 1, 4, 5, and 6 in it. Not so easy to see the solution for markets 3, 4, and 5. You might immediately jump to the fact that you could build a device with features 1, 2, and 3 in the appropriate quantities and sell it to all of them. But whether it's wise to give away to markets 3 and 5 that extra feature 1, given the volumes in those markets, makes it problematic. So even the point of this example, of course, is that even with 6 features in 5 markets, fishing the optimal profit solution out is non-trivial. So with 1,000 columns and 250 rows, it becomes fairly interesting. Compounding this is, of course, again, looking at the three-dimensional problem from the side, that the markets are very dynamic. They don't all hit their max volumes at the same time. We have to generally look at this problem in quarters out at least 2 years, if not 3. And the markets are certainly very dynamic in that time frame. Similarly, looking at the three-dimensional problem from the top, there's the dynamics of developing new features. Given that technology treadmill that gives us smaller and smaller transistors, we have a lot of engineers innovating in feature space. So the Rev 1 and Rev 2 might be USB 2, USB 3. We sometimes face build and buy decisions in this space. We can buy designs for some of the features from other companies and incorporate them. Saves us time, costs us more money, or we can build it ourselves, which costs us time but probably less money. Evan will drill you down into the details of reuse. Given the engineering constraint, if you can reuse some of the features over and over, you can gain some serious advantage in solving the problem. The constraints here are, of course, that in that first example matrix, the features that are in the device have to match up at least with the features required by the market, if not exceed them. The timing is such that you have to develop the features so that they can go into the products. You have to develop the products so that they can hit the critical market windows. And as I've mentioned a few times, engineering resources are one of the fundamental constraints here. The objective, of course, is to maximize profit by maximizing revenue, minimizing both the engineering and the manufacturing cost. So the business problems that we're interested in solving here in that complex three-dimensional space with those constraints are, if you give me an engineering budget, which products can I make to maximize revenue? Or conversely, if you give me a revenue target, which product should I make to hit that revenue target? Sometimes unconstrained. We can solve the problem without the engineering constraint to see what the unbridled opportunity is, or we can solve it with the engineering constraint to see how to hit the revenue target. A very interesting one is if you're an engineering manager and you're supposed to develop a set of features and you have to do them sequentially because you don't have enough resources to do them in parallel, what sequence should you develop them in to maximize revenue, given the market dynamics? I've already mentioned the build and buy decision to you. So really difficult to solve this problem with standard techniques given the size of the problem, the different constraints, the competing objectives, the interrelated trade-offs. And so I'll turn it over to Evan so he can show you how we've formulated that problem and the new algorithm and implementation we use to solve it.
Great, thank you, Carl. So I'm going to talk about the math that underlies this product line design problem. I'm going to use the math to formulate it as a traditional mathematical programming problem, and I'll use that formulation to show how the standard techniques are, how you're going to have a lot of trouble using the standard techniques to solve it. And finally, I'll talk about our solution methodology and the implementation of our solution. So the core problem has three main aspects. The first aspect is that you have to generate a product line. And when you're doing this, you're looking at figuring out what products are going to go into what markets, and also you're trying to schedule your products so that they hit the markets at the critical juncture. This is a strategic question. The next aspect is you have to generate the set of product features. This is more tactical, but when you're generating the product features, you need to design your products so you meet or exceed your market requirements. And you also have to schedule your features so that they're available to support your product availability. And finally, you have to pull together the product line and the product features to optimize everything for profitability. And while you're optimizing for profitability, you have to consider engineering budgets to be sure you don't exceed your available resources. So when you're generating the product line, there's a couple things that you need as input. You need to understand the set of markets that are under consideration. You need to look at your time horizon, and you need to look at how many markets you're able, or how many products you're able to produce at maximum. And the decisions you're making at this stage is how many products to build, which we model as a binary variable beta for every product, if we're going to build it or not. Then we look at when to introduce those products, which is a scheduling variable z, but it's an integer in the time horizon t0 to t, where t0 is the first period that you could ever introduce a product. And the last choice is our three-dimensional indexer. It's which markets you're going to sell your products into. And that's alpha. And for every product P, market M, and time period T, you're making the decision, are you going to sell this product or not? And once you've generated your product line, the next question is what features do you put in your product? So to do that, you have to understand the set of available features, and you have to understand your market requirements. Carl's already shown us the market requirements as the matrix of markets and features. And so D is just that data input. So for every market and feature, how many units is that market interested in? And the decisions we're making at this point is how many units of the feature to put into each product and when to schedule each feature. So pulling together the product line and the product features, we can start talking about profitability. To understand profit, we have to have a notion of market volumes and prices. We have to have rules to define how much our features are going to cost in terms of engineering. We have to understand our product engineering cost and our feature manufacturing cost. So if you pull those together, we can start looking at profit. So profit is revenue and engineering, or revenue minus engineering. And revenue is it's a complex formula, but really it's just the volume multiplied by the product's gross margin. So alpha times V is how many units you get for a given market. If alpha is 0, you're not getting anything for the market. If alpha is 1, you're selling into it. And the second term is the price the market is willing to pay, subtracting out the cost of the product, where the product cost is the cost of all the features multiplied by the number of features you get. So that gives you the revenue portion. The engineering portion is composed of two parts. The first part is your product engineering, and the second is your feature engineering. So product engineering is just the cost per product that you're engineering multiplied by the total number of products. And the feature engineering is a special function that involves reuse, which I'm going to go into some detail now. So reuse is a concept that you can get more bang for your buck if you plan your features in the correct order. So the basic concept is if you develop feature 3 first, you might be able to get some synergies when you develop feature 4. So you might be able to develop that feature cheaper and more quickly. And the critical concept here is that you can't get reuse unless you have a good feature plan. So if I shifted feature 3 out and feature 3 and 4 were being developed in parallel, I would not have a reuse opportunity. So you can see the reuse function is going to be highly complex and it's going to be time dynamic because it's highly dependent on the orderings of all the feature developments. So to illustrate this, I have an example reuse function. So in words, the function is I'm going to group my features into groups of similar features. And if you develop a feature in the group, then the next time you develop it, you get 50% reuse. So it's a fairly simple explanation. But if you try to model that mathematically, it's more complex. So I have 5 features in 3 different groups. Feature 1 is in its own group, so it has no reuse opportunities. Feature 2 and 3 are in group 2, and feature 4 and 5 are in group 3. And if you look at feature 2, its reuse function depends on when feature 2 is scheduled, which is Y2, and when feature 3 is scheduled, which is Y3. So you can see the reuse depends on when all the features are available. And I have a general form of that function. You can see it's highly nonlinear. So pulling all these pieces together, I can show you the full formulation as a mathematical programming problem. The objective is to maximize profit, which is just revenue minus engineering cost. We have a whole set of constraints. Most of them are infrastructure. I'm just going to highlight the key ones. The key constraint is the market satisfaction constraint, which states that every market has to have its requirements met or exceeded. And the other critical constraint is the resource constraint, that in every time period you can't exceed your supply, which is I think the sixth constraint down there. So looking at this formulation, there's a couple challenges you're going to run into if you try to solve this using traditional techniques. The first is there's a large number of nonlinearities. The reuse function itself is highly nonlinear. The objective function has a nonlinearity in it, and most of the constraints do as well. The second challenge is that most of the decisions are either binary or integer decisions that you have to make, and there's a large number of these. And the final thing is just the nature of the problem as a three-dimensional problem. If you increase the problem size to be something past a very small example, it's just going to blow up in terms of complexity. So if you combine all these factors together, you'll see it's difficult to solve this problem using traditional techniques. So our solution method is twofold. We start by integrating different techniques from OR disciplines, and we pull them together to get an integrated view of the problem. So we borrow from job scheduling, from set covering, from portfolio optimization and dynamic programming. We pull these all together and we get an integrated view of the problem. And then on the one hand, while we integrate, we also decompose the problem into simpler steps that we can solve. And we decompose the problem along the same three axes that I defined it as. So we start and we create an outer strategic algorithm whose job it is to generate the product line. Then we have a set of inner tactical models. They're either heuristics or mixed integer programs, and they solve for the optimal feature sets. And finally, we pull everything together and we do our financial optimization back in the genetic algorithm using the fitness of the genetic algorithm. So looking at this as a solution flow, we can see the first step in the decomposition is to design our product line. So that involves coming up with a product release schedule and coming up with product to market mappings. The next step is to feed that in on a per product basis into our inner tactical algorithms, which actually do the feature set optimization. So product by product, you go through and you optimize the set of features. You determine your feature schedule and your feature reuse. And once you've done this for every product, you can go back and pull everything together and evaluate the financials of the entire product line. And you can evaluate your resource constraints. And at this stage, you let the genetic algorithm use selection to select the most fit solutions that have the highest profit. And you use the mutation and crossover genetic operators to come up with new product release schedules and new product to market mappings. So talking a little bit about how this is implemented. The outer layer, like I said, is a strategic genetic algorithm, and its job is to create the product schedules and the market to product mappings. So the way you create a product schedule is you generate a random set of product schedules, and you order it chronologically. And what you do is some products you randomly turn them off. So you say their availability is -1. And you do that to model using fewer than the maximum number of products. And you have two different ways of generating this project schedule. The first is to use mutation, where you just take an existing one and you randomly apply a permutation. So you either push some of the products out or pull some of them in. And the second is to use crossover, where you're going to zip together two existing solutions, and you're going to generate a new solution that has some attributes from both of the parents. And once you've generated the product schedules, you can now create market to product mappings. So what you do is you go through each market and you randomly decide, are you going to cover this market or are you going to skip it? If you cover it, you select one of the products from the available list of products at random. So once you have this information, you can feed the product line information into the inner tactical algorithms and actually optimize for the set of product features. So we can determine what features to put on the product because we know what markets the product is now supposed to go into. And so in general, there's two different methodologies you could use to cover your requirements. The first is to cover your requirements with the minimum manufacturing cost possible. The second is to cover your requirements with the minimum engineering cost possible. So what we do is we randomly allow the algorithm to pick between the two options, and we let the evolutionary process pick the best solution for a given situation. And once you have your product features, you can back out your feature schedules because you know when the products need to be available. So based on that, you can schedule when your features need to be available. And the last step is to evaluate your reuse. And I mentioned earlier that you had to solve the products in chronological order, and that's it's related to dynamic programming. If you want to evaluate the reuse, you need to do it in chronological order. To know what's happening in time period t, I need to know everything that happened in time period t-1, t-2, all the way back to the first time period. So it's important that you solve this in chronological order. So once you've solved the inner algorithm for every product in your product line, you can now pull all the information together and evaluate the total financials. So the first step to do this is to look at your resource constraints. So actually calculating the resource constraints is easy because we already looked at the reuse. The difficult thing is modeling your engineering constraint. So we chose to model our engineering constraint as a soft constraint rather than a hard constraint, and we have two reasons for doing this. The first is that we're doing a strategic optimization, and we want to avoid the situation where you lose out on a good solution because you're $1 over your budget. And the other reason is that it really simplifies the fitness of the genetic algorithm if you model it as a soft constraint. And so we followed a Lagrangian penalty approach that you could think of as an overtime cost. So if you exceed the available resource pool, you pay an overtime fee for every unit that you exceeded by. And so that the evolution will tend to pick solutions that exceed the resource supply by as little as possible. But it also lets you trade off, in some cases, exceeding your resource pool by a little bit in order to get a much better solution. And once you've evaluated your resource constraints, you can calculate the fitness of your solution by looking at the profitability and subtracting out these resource penalties. So when it comes time to implement this, this algorithm in practice, we have to deal with the fact that planning is very strategic. And because of competitive situations, because of current commitments, because of strategic market opportunities, there's a lot of things in the solution that need to be fixed down, and you don't have the opportunity to solve with a clean slate all the time. So what we do is we allow the solver, or we allow the user to pin down parts of the solution, and the solver will solve with the remaining degrees of freedom. So what this would look like is you could take a product and you could lock it in and say this product must be available in this time period, or these features must be on this product, or we must enter these markets because they're strategic. And because of our custom requirements to have this pinning capability, our custom evolutionary process where we have our own crossover operations, and just because of the general solution flow that we've designed where we have an outer layer and an inner layer, we had to do a custom implementation. We evaluated some commercial genetic algorithm tools, and none of them gave us the flexibilities that we needed to create this implementation. So you can see the solver is part of a larger decision support tool suite. Everything in light green was implemented by me in C#, including the solver. The solver is roughly 90% of it is this outer strategic layer, and then 10% of the solver is calling into Cplex to perform those mixed integer programs that optimize the features for either minimum cost or minimum engineering. So now Carl's going to come back and talk about the business benefits of this implementation.
So deploying this custom solution has had quite an impact on the business process that we use to perform this. Before we had this tool, each individual product group in each of the product divisions essentially had their own spreadsheet, all different from each other, their own local data. With that, they could, of course, look at the local view of their product in their division, and there was very, very difficult to do any kind of what-ifs with that spreadsheet. Now, of course, we have one tool that's suitable to look across all of our divisions and all of our products, giving a holistic view. The tool currently handles all of the hardware features. We've just in the past month or so rolled out the software part to capture all the software drivers for the hardware bits as well. And of course, given the math that Evan's just shown you, it's quite easy to play out a number of what-ifs. The engineers like to play out what-ifs of, well, this feature is scheduled for here, but what if it slips a quarter? What if the forecasted volume in this market is half what the forecasters tell us, or double? Lots of what-ifs to play here, given the dynamics of the market and the dynamics of the features. Of course, using local spreadsheets, it was pretty difficult, point 4 in the before, to get the various people who were involved in deciding the product line design and schedule to agree on things. And even when they did, there was little if any, local or global optimization in the context of reuse. What we've seen now, and I'll show you the users that we now have with the deployment. We're seeing much more collaboration in decision making between these various competing objectives, looking at more global optimization of our profits. Increasing reuse, difficult to give you a baseline here, because the reuse between even between products in the same division, let alone between divisions, was so low. I have trouble giving you a baseline. But in the months and quarters that we've been using it, we're seeing reuse increase at 5 to 10% per month, which is quite a dramatic result. We've been working on this for about 5 quarters. You see an exponential rise up to, we have 133 users of the system now. As we give more and more presentations to product groups, as word of mouth goes from engineer to engineer, the tool is getting used more and more. The most interesting thing for us is we actually now have users in all 9 of our product divisions. You see Division 1 was an early adopter. Division 2 is close on their heels. Divisions 3, 4, and 5 are starting to get with the program. The other dissection of the data shows that we have a number of users from the different functions that it takes to pull this all together, from the strategic planners, from the project and program managers, from the design engineers, from the marketing folks, et cetera, et cetera. And it's always nice to collect comments. In yellow, finally working with the transparent system. In orange, seeing where the synergies exist between the products. In green, up in the corner, how we can optimize our market coverage. So we have a complex 3-dimensional problem with a dynamic market, a dynamic set of features. Very difficult to solve with existing techniques. Evan has developed and implemented a custom solution to the problem. So far, the users are pulling it into the organization. We hope over time, we're probably 3 or 4 years away from having this deployed across everybody that needs to use it in the company. We believe that this system will become crucial to Intel's continuing success. And with that, I'll stop. Thank you for your kind attention. We'll be happy to answer questions.